Welcome back to Biopsych Lectures. In this video, I'm going to spend time talking about the action potential. For this, I want you to be able to explain how the movement of ions produces the action potential. I want you to explain the physical basis of the all or none law. Now, for the action potential, you'll recognize this from the last video. Here we have our neuron at rest. And as you can see, at rest, the potential is minus 70 millivolts. Remember, I'm not showing it, but here we've got our cell membrane. We've got ion channels through it. Yeah, everything is set up at rest. Now here, in this, the first step for the action potential or nerve impulse is something, and I'm being vague here, something excites the cell. And there's many different ways the cells can get excited. In the central nervous system, probably the most common is glutamate is going to excite the cell by allowing some sodium to come in. You know, these are completely different channels. How this happens, we'll worry more about later when we talk about synaptic transmission. But suffice it to say, some sodium comes into the cell. Now, when sodium comes into the cell, what happens to our separation of charge? Remember, we got a lot more positives outside than we do inside. So if a little bit of sodium starts to come in, what's going to happen to my resting membrane potential? My separation of charge is going to get smaller. So instead of minus 70, I'll be at minus 60 millivolts. If that keeps happening, I'll be at minus 50 millivolts. Okay? So step one, something excites the cell. In this case, for example, some sodium comes in. We get less negative. That's going to be a depolarization. Okay, so whenever I say excitation, I'm talking about depolarization of the membrane potential. Now, once that happens, as I said, the cell becomes depolarized. At minus 55 millivolts, and this is a typical value, so I want you to remember that. At minus 55 millivolts, special voltage-gated sodium channels open. What that means, gating has to do with what open closes. Okay, so voltage-gated means it's the voltage, the membrane potential, that causes those to open. Later, we're going to talk about ligand-gated. Ligand is going to be something that binds to it, so something will bind to it and open the channel. Okay, those are separate ones. Right, but here we're talking about voltage gated. So when the membrane potential hits minus 55 millivolts, special channels open up. Now, when these channels open up, what happens? Remember, the chemical gradient and the electrostatic gradient are going to drive sodium into the cell. So at this point, sodium is going to come rushing into the cell. Potassium, at this point, those channels are still closed. We still have our tiny little leakage, but not much potassium moves. Now, as that rushes in, what's going to happen to our membrane potential? Think about that for a second. Remember, I'm taking positive charges from the outside and moving them in. Okay, so the outside's becoming less positive, the inside's becoming more positive or less negative. Okay, so this membrane potential is going to continue to get toward depolarization. Minus 20, minus 10. Okay, now what happens when the amount of charge is equal inside and outside? Now my membrane potential is 0. In actuality, that only happens for a split second. Now, as sodium keeps rushing in, what happens? If we keep going, I'm going to have more positive charge on the inside than the outside. So I'll have separation of charge. It'll start out relatively small. But in this case, what should the sign be? Now I've got more positive ions coming in, so it's going to turn positive. Okay? So I want you to remember at minus 55 millivolts, voltage-gated sodium channels open up. Sodium rushes into the cell, becomes even more depolarized. And in fact, the membrane potential becomes positive. All right. Now, somewhere along the way, voltage-gated potassium channels are also going to open up. Now, when potassium channels open up, what happens? Well, the electrostatic force, right, at this case is going to be positive, so that's going to repel. But in addition, the concentration gradient is going to drive potassium out. Okay, so there's a time where I've got sodium flowing into the cell and I've got potassium flowing out. When this situation occurs, sodium wins. Okay, so the flow of sodium in is so much faster than potassium out that we continue to accumulate positive charge on the inside. Okay, it slows down a little bit, but not much. Again, the flow of sodium is so much greater. Now, in the next step, we're going to close these channels. When the sodium channels close, now what happens? Potassium continues to rush out. Now, in that case, right, there's no sodium flowing, so potassium kind of wins. Okay, so what ends up happening there, in this case, is that potassium is going to take positive charges out of the cell. So the inside will be less positive. That's the same thing as more negative. So instead of, say, plus 30, now as potassium leaves, we're going to be plus 20, then plus 10, then 0. Then we're going to repolarize, right? Minus 10, etc., etc. Okay, so this potassium is going to stay open for, potassium channel is going to stay open for quite a while. Potassium is going to flow out of the cell until eventually we get back around our membrane potential, our resting membrane potential. Now, one thing, these stay open a little bit too long, so we actually are going to end up getting a little overshoot. So instead of stopping at minus 70, we're actually going to go to minus 75 millivolts. Then the excess ions are going to flow away. We'll go back to rest. Okay. So as I said, a little too much potassium rushes out. The cell membrane becomes slightly hyperpolarized because a little too much potassium has left. What actually ends up happening is then at the time of this, in this extracellular fluid, the excess K is going to diffuse away. So when it diffuses away, now it's no longer separating charge across the membrane, right? So if this potassium ion leaves and goes way far away from this cell, it's no longer contributing to the electrical potential here. Okay, so some of that potassium excess diffuses away, and then we're going to go back to our resting membrane potential of minus 70 millivolts. Okay, so that's basically the action potential start to finish. I'll show you the timing and a few more diagrams in a minute, but essentially this is what happens to send the message from one part of the axon to the end. You're going to do this over and over and over. Now, here's a diagram showing things a little bit differently. Here on the x-axis, we have time. And I want you to realize, 1 to 2 milliseconds, we're completely done. Right? In fact, the number I want you to remember is 3 milliseconds. Okay, that's about what it takes to fire an action potential and then go back to rest. About 3 milliseconds. All right, and then here we're going to look at the electrical potential. Here, we're going to start at rest. Now, what happens here in this region? Remember, we get that excitation. Okay, what excites the cell could be many different things. Now here you can see there's a change in the slope of the curve right here, right? So here, this is where those sodium channels open. Okay, sodium comes into the cell very, very quickly. That's going to cause a massive depolarization. Now somewhere in here, don't remember the exact voltage, just remember somewhere in here is where the potassium channels open up. So I told you at this point right here, I have both K and sodium flowing. Okay, but what happens to my potential? As I said, right, it continues to get more positive because sodium wins. Right here, what happens right here at the peak? Right here, those sodium channels snap shut. Now what happens? Now from here on, it's only potassium leaving. Okay, potassium's leaving. Now as potassium leaves, what happens? All right, we get less positive. Now, a couple people sometimes got confused here. During this stage, both the concentration and electrostatic gradient are driving potassium out. From this point on, though, right, diffusion is forcing it out. Electro is forcing it in, right? Now, who's winning? Right? This is why I say the force of diffusion is much stronger, because the force of diffusion is driving the potassium into the cell. Okay, that's why, potassium out of the cell, which is why we continue to get that efflux and hyperpolarization. Now, you can see we get a little overshoot here. Those ions are going to diffuse away, so they no longer contribute and will restore resting membrane potential. Okay. Now, this basically is just showing what I was talking about in terms of a time where both sodium and potassium ions are both flowing. Right here, right, what allows sodium to flow in? Opening of those channels. So right here, the sodium's flowing in. If you look at the rate of exit of potassium, right, you can see it starts later. That's when the voltage-gated potassium channels open. Right? It lasts longer, which makes sense, obviously. But you can also see how much lower it is than the rate of sodium influx. Okay, that's why sodium wins. This is a great diagram. I strongly recommend that you be able to draw this and reproduce this, and that you be able to explain each of these points. This is basically everything I just told you. Don't worry as much about this lower part. We're not going to concern ourselves with ion permeability and the flow of ions per se. But this I want you to pay attention to and understand. So here we are, right, at rest. Sorry about that. So here we are at rest. Now, right, we got a depolarizing stimulus, that excitation. Here, the voltage-gated sodium channels open up. So we got rapid entry of sodium in. Now, somewhere along here, okay, so like 4A, is where the potassium channels open. Okay? At 5, at the peak, this is where sodium closes. Okay, so here I want you to understand a little more detail than they have in this diagram. Somewhere along here, the potassium channels open. Okay, so there's a short period of time where both the sodium channels and the potassium channels are open, but my membrane potential continues to get more positive. Okay, the sodium channels close here, right? Potassium moves out. Somewhere down here, right, we're a little bit further because those potassium channels stay open a little bit too long, right? They're going to close, and then diffusion is going to cause the cell to return to the resting membrane potential. Yet another diagram showing the same thing. Again, make sure you understand this. If you do that, you understand the action potential pretty well. Now, with the voltage-gated sodium channels, I just kind of want to show you how they work. Voltage-gated potassium channels work in a similar way, so I want you to understand the concept. Now, there's going to be basically three phases. One will be closed and primed. Okay, so these are ready to go. Second state is open. The third state is inactivated. And here I'm going to use the word refractory. Okay, and we'll talk about the refractory period later, but it's important for you to understand the physical basis. When the cell's at rest, the voltage-gated sodium channels are closed, okay, but they're ready to respond. You can see, right, the shape of the protein is such that these ions can't flow. They're going to bounce back out. Nothing's blocking it, though. Once it opens, we're good. Now, when we get a depolarization, one of the things to remember is electrical fields change the shape of proteins. Okay, so when the electrical potential here changes, it's going to alter the shape so that now the pore is open. Okay, and you can see then things are going to be able to come in. Now, once this opens, ions are going to flow, okay, and then a timer starts. These are going to stay open for a short period of time. Once that timer goes off, they're going to close. Now, they don't go back to their closed and primed shape. In fact, they go to a refractory shape, an intermediate shape, where they're inactivated or refractory. So in this case, what stops the flow of ions is actually another change in shape so that the channel's blocked. Okay, so here you can think of it, this is open, right? But the ions can't flow through because there's a gate preventing them from going. Over time then, when the membrane potential is restored, time goes off, we're going to cycle from this back to this state. Okay, so three states of the voltage-gated sodium channel. Closed but ready to respond, open, or refractory. Okay, and for this class, that's it. Now, one of the things we talk about is the all or none law. Okay, the reason we have an all or none law has to do with this. There's no kind of open state. Either it's completely open or it's closed. Okay, so we don't regulate a little bit of sodium coming in or a lot of sodium coming in. Either sodium comes in completely or it doesn't. This part you can think of like flushing a toilet. If you hit it, there's no kind of flushing it really, right? Either it flushes or it doesn't. Same way with this voltage-gated sodium channel. Okay, all or none. So the physical basis of that is the fact that we can't have these sodium channels open a little. They're either fully open and sodium rushes in completely, or they're closed. Nothing in between. Okay, so that's a quick summary, a quick overview of the action potential. I will ask you in a series of assignments to and example questions what would happen if I change some things, and that'll help you understand that will help you know whether or not you really understand it. All right, thank you. See you in the next video.